So first of all, I want to thank IDC for giving Microsoft an opportunity to be here and present our part of the story. I was specifically told not to give a sales pitch and talk about technology and trends. So I'm going to try to do that. And I do have some slides, obviously, about Azure because that's what I work on, engineering strategy there. So let's get started. So when we look at a big compute ecosystem, there are different kind of people involved, whether it's on-prem or in the cloud. You have cloud providers, hardware manufacturer, OEMs, network providers, storage, you have operating system tools, you have schedulers, end users, and commercialized suites. That's kind of at a very high level, the way I look at the ecosystem, right? And every party has a part to play in each of them. The most important is the end user, and I see very few end users here. I wish I could talk to them more. So when I'm talking to my customers or our customers, and what we hear from them is most of them are talking about, well, we want to use HPC because we want to develop our product faster. I come from a manufacturing background, is to run crash simulations in automotive. The reason auto OEMs use HPC because they want to reduce physical testing and do as much simulation and develop products quicker. A lot of them want on-demand compute. A lot of crash engineers or NVS, durability, computational fluid dynamics engineers want to use DOE or optimization. They want to do thousands of runs, generate terabytes and terabytes of data, and analyze the trend for the underlying physics that they're trying to simulate. They're always restricted by compute. I mean, even if you have 50,000 cores, a lot of time it's not enough because 5,000 engineers are using the system. Imagine if you submit 1,000 jobs to do a DOE full factorial, it's going to take forever to finish. They want to do high fidelity. The models are getting, when I started doing simulation, a 1 million element model for crash used to be like a big deal. Now it's pretty standard to run 10, 20 million element models. We just ran a CFD job with 500 million elements on one of the CFD codes, and we see very good linear scaling. We'll talk about that. So the models are getting bigger day by day. A lot of users want the control. They want on-demand, right? So I should be able to go provision my machines, I should be able to run my job, and I should be able to shut the cluster down. We really call it a job per cluster and not a monolithic cluster that most of us are used to see in our on-prem data centers. They only want to pay for what they use, and they want mobility. So if I have access to the cloud, let's say I'm on the road, I'm visiting my supplier that manufactures seats in automotive, and I'm at their factory, and I want to quickly submit the job, I want to change the parameter in my input deck, I should be able to do that seamlessly through a normal SSH connection in the cloud. I don't have to go through VPN, blah, 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 a lot of other stuff. So mobility is important, and remote visualization kind of plays into that with our GPU strategy. So this is what I hear from the end users, right? An example of that, we have a customer, Hendrick Motorsports, NASCAR. Some of the big names in NASCAR are those drivers are on the payroll with Hendricks. And they ran Star CCM Plus in Azure on up to 1,024 cores. And Hendricks relative to auto OEMs or some of the national labs that are here, they're fairly small, right? Their total IT budget is like maybe a few $1 million. They can't afford to purchase 1,024 clusters and just keep them around, just whenever the race is there or when they're changing the design. So truly on demand, and that's why they use it. Then there are cloud providers, right? So what we call hyperscale. David was here just before me talking about hyperscale. We think there are only really 3 players in this space that can truly do hyperscale, but it requires billions and billions of dollars of investment, right? It's AWS, Google, and Microsoft. And I have a slide. We have about, over the last, I would say maybe 4 years, close to $15 to $18 billion investment in data centers. So obviously what that does is you have enough competition in the market that drives the cost down. If anybody has observed trend for blob storage in the cloud, The prices continue to decline for last over, I would say, maybe 4 years. Now they have started to taper off a little bit, but it's so cheap to store data in cloud. It's not even funny, right? So that's good for consumers, that's good for customers. And a lot of cloud providers, what I see is trying to move to higher level services. Microsoft is obviously trying to do its part, but cloud providers are trying to come up with not just infrastructure, like network compute and storage is kind of given nowadays, right? You can come up and spin up 5,000 cores and run an MPI job, and I'll talk about that, how we do it. That's pretty much given nowadays. That's like, that innovation has left the station. But value-added services, so if I'm an end user, I want to do end-to-end. So I should be able to do pre-processing easily in the cloud. I should be able to submit jobs easily, truly on-demand and automated workflow to do your entire end-to-end design. How can I execute that in the cloud? That's what I mean by higher level services. So you will see a trend, I feel, going towards higher level services in the cloud eventually. There's still some challenges. Last mile is always a challenge. So Microsoft has its own offering called ExpressRoute, which is MPLS connectivity directly onto your MPLS network that gives us a maximum bandwidth and relatively lower latency. We also try to localize our data centers in the region that we go. We have edge networks that we call, all kinds of things, but still connectivity. If you want to upload a petabyte of data in the cloud, it's a problem, right? So latency is also important. Intra-node latency to run MPI jobs at scale, it's, a lot of us here believe that that's true HPC, right? And now talking a lot about big data, but ultra-low latency is super important, and that's a challenge. And then workflow automation for higher level services, as we talked about. So these are challenges I see. Another big important part of this ecosystem is commercial ISVs. Obviously, if you're working for a national lab or a university, you might have open source code, or you might have developed it yourself, then it's a different. But most of the commercial industry uses commercial ISVs. And a lot of these ISVs, with my interaction, have been kind of a little bit slower to adopt to the cloud. And they have their own challenges and own reasoning, but it's still a relatively niche market. The industry I come from in automotive, a lot of simulation providers have been kind of worried that how they're going to monetize this utility model, right? Because my user wants to pay for per hour of software they're going to use, versus I'm used to leasing it over 1 year or a paid-up license, stuff like that. And we as a company, Microsoft, Office 365, we went through the same transition, right? We were used to selling Office licenses per PC, collect your cash and be happy with it. We had to change our business model to Office 365, where we are charging per user per year. So we went through similar pains, and we're trying to, when we work with ISVs, we try to bring some of that experience to them and try to encourage them to look at the longer picture. The more cores users are going to run in the cloud, the better it's going to be. At the same time, running very large scale, design of experiments or optimization. So let's say I'm running a CFD code on 1,000 cores, and I want to run 500 jobs like that. Now, if my license costs keep exponentially increasing, that thing is going to be 100 times more expensive than buying a cluster on-prem. It's just ridiculous. So, but I see a change in this market slowly. ANSYS recently announced their pay-as-you-go license. Star CCM from CDADAPCO has a utility-based licensing per hour. So there is change happening in this market, and it's inevitable. So I think we're moving in the right direction. And some of these commercial ISVs are extremely crucial to make this cloud adoption really mainstream. And my opinion is that we are moving in that direction. And they have their own challenges also, right? So you want to make sure ISV's intellectual property is protected and they're able to monetize, because we don't want these people going out of business. So it is critical. So they're taking their time, but they're moving in the right direction. Good example of that is Schlumberger. So we work with Schlumberger very closely. Their application Intersect for oil exploration is offered software as a service on top of Azure. So it uses true MPI. It uses our low latency RDMA connectivity, and they offer that as a service. So if anybody here from oil and gas industry, you can go check it out. Let's talk a little bit on Azure. So this is my sales pitch now. So I try to keep it as technical as possible. Azure, this is the great thing about cloud, right? 500 features released in last 1 year. It's just phenomenal pace of innovation. I joined the team, I've been with Microsoft for 10 years doing different roles, but I joined the HPC team and I said, I'm only coming on the team if you let me work on Linux. And if you let me work on Linux RDMA. And he said, absolutely yes. So we launched Linux RDMA July of last year. Since then, we have done a lot of great things, and we'll walk through some of them. Here's just quick statistics on Azure. About 90,000 new customers, subscriptions, 1.5 million SQL databases. It's just 90 trillion storage objects. We have authentication system called Azure Active Directory. About 551 million users, and this just increases by leaps and bounds every year. The 90 trillion storage objects, it maybe took us 4 years to kind of double that from 45 to 90, but we project that within next 2 years it will double to like 180 trillion objects. It's just crazy, phenomenal growth. What is Azure? Oh, sorry. Go one. Azure is a bunch of services, but really at the heart of it, it compute, storage, and networking. Azure was born as a platform, as a service kind of platform, so we do that really, really well. And now we do infrastructure as a service as well. So the HPC piece that I'm going to talk about is kind of really at the bottom here, left corner, compute, storage, and networking. And then there are obviously services built on top of that. For example, if you use Office 365 at your company, your credentials are authenticated through something called Azure Active Directory. So if anybody is familiar with Active Directory on-prem, you used to stand up a Windows server, you have Active Directory role, you add a domain. Now all that can be done in the cloud as a service. So these kind of value-added services on top of that, there are like 70 or 80 different services, we just continue to add them, is what we have. One of those interesting services, which I'm not going to go in very detail today, but I thought this is a low latency, InfiniBand kind of crowd, so I'm not going to talk about a whole lot. It's called Azure Batch. Azure Batch, think of Azure Batch as a HPC as a service, where you get a cluster per job on demand. And it's available through different runtimes, it's available through APIs, it's available through CLI, and we have done scale testing. I'll just keep, in the spirit of cloud, I'll keep throwing numbers. We have done scale testing on an insurance actuarial modeling up to 100,000 cores, for example. So Azure Batch is one of those services in Azure that contributes to HPC as well. And that this is one of the largest European banks that we work with for managing the risks and compliance. They use Azure, and they use 20,000 cores, that kind of scale, and they actually do it all on Windows through our scheduler called HPC Pack. So they burst on demand. They have a data center on-prem, but they burst to cloud when they need to, especially at the end of the quarter, at the end of the month, when they have their regulatory reporting requirements. Let's come back, let's dive in a little bit deep into what is our big compute philosophy or HPC. We take pride in saying that we call it no compromise HPC. We can obviously debate what that means. But what does it mean for us? Low latency we think is extremely crucial. There is a market for non-low latency type workloads, obviously embarrassingly parallel. But anything that is tightly coupled MPI bound needs low latency. I mean, there's no surprise on that. So we strive to give you lowest possible latency we can. Dedicated non-blocking network for MPI, obviously through InfiniBand. Close to bare metal performance. So we run a virtualized environment, but if you talk to our people that do benchmarking on Linux on top of our hypervisor, you'll see very, very minimal overhead. We obviously believe in resilient parallel file systems, so we have different storage options, but one of the recent developments is Lustre from Intel. The parallel file system is available on Azure now with our premium storage, and we see really, really good performance running MPI workloads for scratch IO, right? Because when you're running 500 million cell model, you're going to get a lot of I/O. Depending on the application, we use Lustre for that. We believe in high-frequency processors, so I cannot publicly talk today what is our next processor is and configuration, but if you want to see me in private, I can give you the details. We try to strive the fastest processors we can find. Large memory fat nodes, we're going to double our memory footprint for our compute nodes very, very soon. SSD-based local storage, so up to 2 terabytes of local scratch on top of global scratch if you need. Coming from Microsoft, I joined the team to work on Linux. We released Linux RDMA July of last year. So Linux and Windows, SUSE Linux, CentOS 6.5.7.0.7.1, and soon Red Hat. Red Hat is already available in Azure, but Red Hat on RDMA will be available pretty soon. And then I can provision entire Lustre cluster with SSH trust without a scheduler. Now soon scheduler will also be there. I can provision 5,000 cores in 10 minutes. Completely automated cluster deployment. So that's what we mean by no compromise. Let's dive a little bit onto virtualized RDMA. We use network direct stack, and we have developed our own stack called Endure. We support Intel MPI, obviously Microsoft MPI on the Windows side, and we have a platform MPI in prototype from IBM. So we work extremely closely with Intel. We found them very open to work with us. Different knobs available in Intel MPI. We don't support OpenMPI yet. If there's a significant requirement from anybody in the audience, please talk to me. We support only certain pair of verbs, and we use DAPL transport for MPI communication, which is not supported in OpenMPI. And if there is significant requirement for it, we're willing to contribute to the open source OpenMPI community and develop the DAPL transport. OpenMPI used to support DAPL, but they dropped it. So anyway, it's kind of a quick architecture. Basically, VSP, I don't know if guys in the back can see, but basically VM buses. So you have a host operating system and a guest, and basically host is what is running the hypervisor. The guest is either your Linux or Windows in the guest. And those guests kind of need to establish connectivity and register addresses. So we do that through VM bus, the VSPs and VSC talk. And once that connection is established, then the operating system gets out of the way so the application can directly talk to the MPI stack and the network. And that's how we get low latency through our RDMA stack. What we offer today, our hardware is getting a little older. So don't raise eyebrows because we have a new hardware coming in, and I can talk to you in private what that would be. But today we have what we call A8, A9 instances that are InfiniBand enabled with RDMA interconnect. These are Sandy Bridge 2670 processor with 16 core each. Another thing about no compromises, we don't do hyperthreading for our HPC nodes. So you have 1:1 CPU mapping or core mapping. You have 16 core on the box. If you do A9, a VM with 16 cores, you get 16 cores. And that's how we deliver close to bare metal performance. We actually have 112 gig of memory, DDR3. I know it's a little bit old, but this is a very, very balanced system that what we found. The CPUs are not waiting for network to catch up and things like that. So even if it is Sandy Bridge, if you compare Sandy Bridge to Sandy Bridge, you'll get very close to bare metal performance. We have QDR InfiniBand dedicated for MPI traffic only. A lot of time people ask me, I'm using Lustre, can I use InfiniBand? We want to reserve QDR InfiniBand traffic for MPI only. We have a 10 gig front end through TCP, and we use that for other kinds of traffic for Lustre storage and things like that. We are bumping that 10 gig to 40 gig in our next front end for storage and other traffics. We have 2 terabytes of scratch per node. Again, it's available, different flavors of Linux, and it's available in 7 regions around the world, 4 in US, 2 in Europe, 1 in Japan, and that footprint will increase very, very soon to go even more global. And as I said, I actually had a slide and I kind of deleted it because I was told not to show that. But we are working on next generation, which will be rolled out in a couple of months. I can talk about that. That will be faster processor, more memory, better InfiniBand, just gets better. Let's talk quickly on GPUs. We announced GPUs, so I can talk publicly about it. Don't make fun of the names. It's called NV6, NV24, and NV12. They are what we call V stand for visualization. I have no idea what N stands for. It's there. You have 6, 12, or 24 CPUs. And these are the M60 NVIDIA cards. We are the first ones in the cloud to offer that for remote visualization. And it's available through DDA. And you either get 56, 112, and 224 gig of memory, up from half a terabyte to 2 terabyte of local memory. And then this doesn't have RDMA because these are Viz nodes. It has 40 gig front-end Ethernet. We do have compute VMs with K80s. Again, one of the first cloud providers to offer that in the cloud. Again, they go from 6, 12, 24, and 24R. R stands for RDMA, low latency network, for GPU compute as well. So either you get, let me go back to the previous slide for a second. I do want to mention, you get 1 GPU, 2 GPUs, or 4 GPUs. So you get an entire card, you get half a card, or you get 1 GPU, depending on your workload, what you're trying to achieve. R stands for RDMA, so it will have, in this case, we're testing out Rocky, RDMA over Converged Ethernet. There's a debate on that, the latency, especially through switch hops, can, creep up, and we want to try it. And so we have made Rocky available with RDMA on compute nodes with K80s. Again, here you get 1, 2, 4 GPU cards. Each GPU has about, I think, 2,100 GPU cores. And you go from 112 to 224. That should say 112. It's not 128. I apologize. And then if you don't want RDMA backend, by the way, the RDMA backend is dedicated. You still have front-end 40 gig Ethernet. So you have enough network bandwidth to do anything you want within Azure. The good thing about the GPU visualization, especially if you use our regular A9s or next generation of A9, and then you have GPU nodes right next to it in the same data center. Now, a lot of time people say, I do compute and I have to download all my D3 plot files to do visualization of my crash simulation. I'm not going to download 60 gigs of data per run. Well, you don't have to anymore. Transfer the data. You can map the same Lustre parallel file system onto Viz node, and now you have 40 gig pipe going between machine to machine. You can do visualization and post-processing of your nodes anytime. So it kind of removes that bottleneck of data transfer. So we had one of the largest chemical companies in the world use our A9 nodes with RDMA, InfiniBand RDMA with up to 2.5 microsecond latency. They use that up to 1,600 cores for one job. Now it's okay up to 96, 128 cores, great. Any application will run on Ethernet. Some of them still won't because they just require, depending on the message size you're passing, right? But when you start creeping up into 256, 512, 1024, 1600, 2000, if you don't have latency, you can't run it. It actually will run slower than by adding more cores. So these guys ran up to 1600 core jobs and phenomenal results, and they were able to launch their product in time. It's a quick architectural diagram. I know it's an eye chart. I'll make the slides available online. But here is how we kind of, I don't know if I have. Basically, we have compute nodes here with the head node, dedicated RDMA for MPI traffic, and the rest of the traffic is routed through front-end 40 or 10 gig through a Lustre parallel file system. We recommend that you use Lustre because it's attached. It's like a file servers. You can have up to 16 terabyte per server, and you can have 5 of them. You have an 80 terabyte pool for global scratch. We don't recommend storing here data for months and months. As soon as you're done with your simulation, keep it there for a few weeks, and then move it to blob storage for permanent storage. You can connect to these. Obviously, everything is defined through software-defined networking, as David was saying before. We have VPNs in Azure. So this is like a small cocoon within Azure Data Center that is owned by you. You can port the public ports off, only keep the private ports for internode communication. And you're kind of doing NATing through the head node, right? So You connect that to on-prem using ExpressRoute or VPN. Let's talk about Hyperscale a little bit. Microsoft has more than 100 data centers, but we truly have, for Azure, I would say 28 regions around the world that are 2 times to our closest competition. We have taken an approach of obviously massive data centers, but we have taken an approach of localized data centers as well. For example, we announced a data center in Germany that has a trustee model where German citizens and T-Systems locally manages the data. Nobody outside Germany gets to access the data. Same thing we have done in China. We announced a data center in UK. We have 3 data centers live in India, Canada. We have a DoD cloud that we announced. We have ITAR compliance cloud already that's running out of space because it's so popular. We have data center in Australia, Brazil. We have a 3rd largest private network in the world, and as I said, 15 billion investment over the last few years. So we massively continue to invest, and we run out of capacity all the time because this is so popular and we are expanding like crazy. So now every data center doesn't have HPC, InfiniBand nodes. Today they're available in 7 regions, and soon that will double within the next few months. Tools, and quickly want to talk about Lustre and different storage options available. Obviously you have blobs, which is the cheapest way to store data, but it's kind of useless to do it while the job is running. We have Azure Files, which is SMB 3.0. I wouldn't recommend it for running it for high performance workloads. We are working to boost the performance of SMB, and you can use it through CIFS on the Linux nodes. We have Azure Data Lake, which is for big data, and it's kind of a service on top of Azure Blobs, extremely fast throughput, and there is no limit on your storage account. Blob has a limit of 500 terabytes per storage account, so if you have 2 petabytes of data, you got to manage storage accounts and kind of manage it. You don't have to do that in Azure Data Lake, especially for IoT connected car projects, where we are generating terabytes and terabytes of data per car. Azure Data Lake is a great option because you ingest so much data. And then we have Lustre. So we work very closely with Intel. It's available in Azure Marketplace, complete automated deployment for Lustre. And we do that on our premium storage to provide huge amount of data storage space for Scratch. Quick Lustre architecture. If anybody using Lustre, you're familiar with it. And I'm running out of time. I come from a CAE background, so I work with a lot of ISVs in my space very closely. As you see, most of the solvers here listed, Abacus, LS-DYNA, Star CCM, Fluent, Radius, OptiStruct from Altair, PBS Pro Scheduler, Univa Grid Engine, Intel MPI, you just name it, most of the support is there now. And I have one last slide. This is just hot off the press. We used to do benchmark up to 512 cores. People say, that's like, don't even talk to us, 512 cores. So 1024, so we continue to push the limits. We're not allowed to say the name, but it's a CFD code, running 100 million cell model, very linear scaling, and we'll just continue to push the limits. As I said, we have customers that are running 1,600 core jobs, so scaling is not an issue. I found finally time to run some of these workloads, show you the benchmarks. And we have launched a new site, simulation.azure.com, no www. So feel free to visit that site. Has a very detailed information. You don't have to go from page to find information, which is very typical in large companies. So we created a microsite called simulation.azure.com, and we continue to update it. So with that, I'll wrap up and open for any questions.
Thank you.